the ideal gas equation. Let's take a look here at our bringing all of these laws together. PV equals nRT. This is the official ideal gas equation, which can be manipulated with all four variables in there. The one new one that you hopefully heard about from last year in Chem 1 is R, which is the ideal gas constant. And it's just a proportionality constant like there was in Boyle's law, Charles' law, and all the other ones. Universal gas constant, all right? Also, I put the links in here for the crash courses, although you can Google them at any time. There is an ideal gas law crash course, and he talks very fast, but his examples are usually really well done. The R, the gas constant. What you need to know about R here is there's different versions of R. And this one also, they're putting it as joules, but it could be kPa. Kilopascals. Now, the R's here, they have 4 units with them. So we have our 8.314 liters times kPa over moles times Kelvin, or 0.08206. This is liters times ATM over moles times Kelvin. This is a derive unit, and they make this have all different units in it because you need them to cancel when you do the calculations. The last one, 62.36, this is liters times torr, or millimeters of mercury over moles times Kelvin. So that you could also use millimeters of mercury here. That one is the same value because torr and millimeters of mercury are basically the same unit. Which unit out of all of the R's are different? Is it the moles, the temperature, the volume, or the pressure? Which unit is different amongst them? Volume, moles, temperature, pressure. Anyone? You have these 3 different R values. They have 3 different numbers. 8.314, 0.8206, 62.36. Yes, the one that differs amongst them is the pressure unit. They all have moles, they all have Kelvin, and they all have the volume. What you should see here, different pressures. Different pressures. And because they have different pressures, you have to gauge which one to use based off of the pressure in the problem. So look at what unit of pressure they're using in the problem so you know which one of the R values you should use. Now this is what's on the formula sheet, so you have the R values in front of you for the AP exam. You don't have to memorize them. What you need to do though is be able to apply them correctly to the problem based off of which pressure. The liters, moles, Kelvin, those 3 units are always the same. It's the pressure that makes these numbers change. Why is that one 62.3? Because it's based off of the 760 millimeters of mercury standard pressure value. Here, 1 ATM is the standard pressure value. And then over here, 101.3 kPa is the standard pressure value. So that's what makes these all have different numbers, because they're based off of different pressures. The ideal gas law can be combined, and we can combine them so that we can utilize it instead of knowing the other 4 gas laws. Since R is a constant, this is a constant value, it's a proportionality constant, depending on which pressure you're talking about. R of the original conditions is going to equal to R of the new conditions. So you can set the variables equal to each other. We can do that. So if we have change, we're taking a gas and we're changing the conditions of the gas, where we're changing the pressure, volume, temperature, or the number of moles. You can change all of these 4 different properties of the gas. You can always calculate what it would be under the new conditions. Instead of memorizing all 4 gas laws and by their name, which you don't need to know them by their name, you could use this combined version, and I like the combined version. I just cancel out which variables are constant. So say, for instance, I have a problem where the pressures and the volumes are changing, but the moles and the temperature are not. Well, that's Boyle's law, but I don't really have to know Boyle's law by name. I have to know that it's the pressure-volume relationship that's inverse, of course. One goes up, the other goes down, that idea there. But if I'm quickly trying to do a problem, I can realize, set this up, use the combined, cross off the ones that are constant, and if pressure and volume's changing, that's Boyle's law. If the volume and temperature are changing here, like this particular one, I cross off pressure and moles, well, now I have Charles' law. If I have pressure and temperature, but volume and moles are not changing, that's Gay-Lussac's law. And last but not least, if I have pressure and temperature being constant, volume and moles are changing, that would be Avogadro's law. So combining the variables, this gives you the one formula. You can write it out, cross off the ones that are constant, and know which variables are changing and which ones you need to use without having to memorize the individual gas laws. Like they're never going to ask you a question like, which one's Charles' law? They're not going to ask that. They may ask you if pressure and moles are constant, if the volume is increased, what's going to happen to the temperature? That's a reasonable question because they want you to know the relationship between the different variables. But they're never going to ask you by name which law is which law. Know the variables. The only one that's indirect or inverse is pressure volume. All of the other ones are going to be direct. So pressure, temperature, volume, temperature, moles, volume, all direct. Now we're going to go work some exercises 4 through 6. All right, looking here at 4. What you should have noticed, and some of you were discussing in your groups, that yes, we have a temperature, so I'm going to label that T, we have a volume, we have a pressure, and moles. We don't see any changing variables. It's not like we're going from this temperature to a new temperature. So in this particular case where we are just having the variables, one particular gas, not changing conditions, this is just a regular PV equals nRT problem, where we're just plugging and chugging using the ideal gas equation. Now, before I do anything, of course, I have to add my 273 here, which of course makes this 300K. No, 296K. What am I thinking? 296, that's right. Okay, because 3 plus 3 is 6. There we go. Now, ATM is my pressure, so that means I need to use the 0.8206 liters times ATM over moles Kelvin for the R. This is going to be the R that I need to choose. Now I can plug in my values and solve for my answer. So write out the formula first. This is the amount of work I'd like to see. 25.0 liters. Now we're missing the moles, so we leave that the variable 0.0820. Oops, that's a crazy O. Let me fix that. 6 liters times ATM over moles times Kelvin, and then add in my Kelvin over here. Now the important thing to see and make sure you're setting everything up correctly is being able to cancel. So ATMs cancel with ATMs, liters cancel with liters, the Kelvin cancels with the Kelvin. So when you do the division over here, this ends up being moles in our answer. multiply these two together, then I divide by this one. I hit enter in my graphing calculator, then I divide by this one. So I do it in stages, although you could multiply these two together, just keep them under the same parentheses so your graphing calculator doesn't get the order of operations out of order. So then you would see that the moles are going to be 3.27. Don't forget your unit over here as your final answer, which is correct. Now for exercise 5. A little bit different here. We have a volume. Pressure looks like that's what's missing. Contains kilograms. Interesting. Kilograms is a mass. And then, of course, we have our temperature here. We can go ahead and add our 273, change that over to Kelvin, get our 298 K. The mass. When we're given masses, what can we always do with masses? Always, always. Whenever you have a mass, you can do this. What can you do? Convert it to moles, which is what we're going to need to do here first. And it's kilograms, so set up my little T-chart. Put kilograms to grams, so 1,000 grams equals 1 kilogram. Then grams down here to moles. And if I look up here, this is helium, He, on my periodic table. The molar mass is 4 grams per 1 mole. So here I'm going to put my 4, my 1 mole up there. Now the kilograms cancel, the grams cancel, and now I'm left with moles. Now it's your choice at this point to round it or not round it, I suppose, before you plug it into the PV equals nRT. Shouldn't give you too much of a different value, but I'm getting the 17.5 moles. Now that I have this value, I have my missing N number. So I have volume, I'm missing pressure, I have temperature, I have moles. Now pressure, of course, they didn't define for us which one to use. When they don't define it for me to use, I always use ATM because the ATM pressure values and those particular measurements are smaller numbers, usually. Because millimeters of mercury, standard pressure in millimeters of mercury is 760, and kPa would be 101.3, so ATM is usually the one I like to use here. PV equals nRT, so here, missing the pressure, the volume is 304.1, or 0.0 liters. The moles 17.5. Like I said, you could round it before you do it, but a lot of times they tell you to wait till the very end to round stuff. I'm going to use the, like I said, the ATM one here, and gonna calculate my pressure in ATMs. Sorry, that's not liters on the bottom, that should be moles. Moles times Kelvin on the bottom, and then over here my Kelvin, which I calculated to 98 K. If I did everything correctly, my stuff should cancel. So let's check. Liters cancel with liters, moles cancel with moles, Kelvin cancel with Kelvin. And look, I'm left with my pressure, which is what I want anyways. So the pressure, do the calculating here. Make sure, like I said, if you're entering it all in at once, make sure you have your parentheses in the right spot so it does do the order of operations correctly. And I'm getting 114 ATM. Now, this one has 4 significant digits, this one has 4, but when we add here 273 in, this one's going to have 3 sig figs, so that's why I keep 3 in my pressure. Remember, adding the 273 does ultimately add 1 digit to that original temperature in terms of significant figures. And we got the correct answer. How about that? All right, now, this particular one, different take. At what temperature, so this is a temperature, does 121 milliliters of CO2. This one is a volume. Another temperature here, a pressure, another volume, and another pressure. So that's kind of the first thing I would do. Also mapping out, trying to figure out which equation to use is like, do I have changing variables here? Or am I just searching for a missing variable? I definitely have changing variables. I'm going from one temperature to the next, I'm going from one pressure to the next, I'm going from one volume to the next. So this one would be where we would want to use the combined. P1, V1, N1, T1 equals P2, V2, N2, T2, like so. Now, the only variables that are changing, though, are temperature, volume, and pressure. So I'm going to cross off the moles. I'm not going to use them because they're not telling us the moles are changing. So then I need to go through and label. So at what temperature, and does this original, here's the original. So here's our original volume, our original temperature, our original pressure. If we change the volume and the pressure to these new values, what is that temperature going to be? So this is where I would be missing my T2. This is the one here where I need to change my 27 degrees Celsius to Kelvin first. And that one comes out with the 300 K. Now that I have everything ready to go, I can just plug and chug. I'm going to point something else out to you here. Because our volumes are in milliliters, and if I'm using combined where I do not have R, there's no R to consider, I can keep it in milliliters. The only times where you have to make sure that it's in liters or a certain pressure, moles times Kelvin, is when you have that R value. So in order to use the R value in the ideal gas one, all of the volumes must be in liters because all of the R values are calculated in liters. But since this one, we're not using the R value, we can keep it in milliliters. So now I'm just going to plug away here. Here is my first 1.05 ATM. P1 times my volume 1, which happens to be 121 milliliters. That's this one over T1. And that is going to be 300 K. Over here, P2. P2 is right here. So that's 1.4 ATMs. My milliliter 2, second volume, changing it to that volume over, and of course this is the one that we're missing, our T2. Now when you calculate, you can cross up, I would change, like cross this one up here and make the other one down there. That's what I would do. And multiply this over to the other side. I kind of do my algebra like that in my head, and that way I don't have to rewrite everything down. So T2 equals here, like so, 1.05 times 121 divided by 300. Alrighty. Ooh, that did not work. Okay. Nope, that didn't work either. Okay. Not calculating correctly here. All right. Ah, there we go. I got it. Should have gotten a really large temperature. 969 K. Now the other thing to remember here is they wanted it in Celsius, so I need to subtract the 273. I do that, subtract the 273, and I get 696 degrees Celsius as my final answer. So this one is using all the combined stuff. correct answer. Now, the molar volume of an ideal gas. Ever wondered where that 1 mole equals 22.4 liters conversion factor came from? Well, it actually came from plugging into the ideal gas equation 1 mole, 1 atm, which is standard pressure, and 273, which is standard temperature. So actually plugging in the 1 mole, the standard pressure, and the standard temperature, when you calculate the volume, you end up getting 22.4 liters. And that's why that conversion factor is what it is, but it has to be at standard temperature pressure. And once again, you can see cancellation of the variables, the moles cancel, the atm cancel, and the Kelvin cancel, so you're left with liters. So molar volume, 22.4 liters at STP. That's important because if you see a question where it's at STP, you can use this conversion very quickly, and you don't have to plug it into the ideal gas law. Ideal gas law takes longer. Converting it using the conversion factor is quicker, and of course speed is always of the essence. So if I'm looking at this particular problem, and because we've been hyper-focused on using gas laws and ideal gas law, you might go straight to PV equals nRT. Sample of oxygen has a volume of 2.5 liters at STP. Well, STP is 1 atmosphere, 273 K. So I have those values. I can use PV equals nRT. I can put them in here. So here's pressure, here's temperature, here's my volume. I can plug those in. If I use ATM, I have my 0.8206 number I can put in for R and solve for moles. I can do it that way and then change the moles to grams, so convert moles to grams. It's going to take longer though if I see STP and I go, 1 mole equals 22.4 liters. I can use that instead and just set up a simple dimensional analysis. So and this is oxygen, so I guess I should put that in there. So 22.4 liters would go down here of O2 equal 1 mole of O2. And then 1 mole of O2, because I want grams, I can just convert it directly to grams. You know, and oxygen's 16, so 16 times 2. That gives me 32 grams of oxygen. This, setting up the dimensional analysis t-chart, is much quicker than using PV equals nRT, although you can use it. You would still get the moles, and then you could convert the moles to the grams. You'd still get the correct answer. But it would just take a little bit longer in terms of being able to do that. So liters cancel, moles cancel, left with grams here. When you do the calculation, 2.5 times 32 divided by 22.4, we're going to end up with 3.57 liters of, not liters, grams, that's what I wanted. Yes, I just said we wanted grams. Now, why did I write down liters? That's weird. All right, grams of O2. So part of gas law manipulation is being able to recognize and utilize the quickest method possible to getting the problem done. Derivations of ideal gas law with density. I don't think we explored a whole lot of this in Chem 1, especially in the spring. Now, some people are really good at deriving. Some people, deriving is not their thing. If deriving is not their thing, I just suggest you memorize one of the forms of the equation and then manipulate it from there. But let me show you how it does derive so you can change over ideal gas equation to where you're working with density. Here is our regular equation, PV equals nRT. Wonderful. Now you rearrange it Okay, so you put the volume on the bottom, you have the moles up top, times RT. That's great. But now we know this equation. The moles equal the mass over the molar mass. So for N, I'm going to take out the N and I'm going to plug in the actual mass over molar mass. So times RT over V. If you rearrange or regroup these variables, look, now it's mass over volume. Mass over volume we know to be density. So mass over volume times RT over molar mass. So then we end up with pressure is equal to density times the gas constant times temperature in Kelvin over molar mass. That is one version that you can use. Now, if I wanted to solve it though, so density, solving it for density, I would need to move the variables around. So I'd multiply the molar mass on both sides, then divide by RT. And you'd get this version. Pressure times molar mass over ideal gas constant times temperature gives you the density. So this would be number 2 version of substitution and moving variables around to solve for density. Both of these have density and molar mass in their equations though. So you can solve for either one of these. You could solve for density or molar mass if you derive the ideal gas equation from here. Now, this is what they give on your formula sheet. They do not give you this version of the equation. That's why they expect you to be able to derive it. They do give you this one, and they give you this one on your formula sheet. So they're both there and ready to be inserted as needed. But they don't give you these forms of the equation. They expect you to be able to think through it, substitute in mass over molar mass, and substitute in the mass over volume will give you the density. So that's 1, 2. Now, if we wanted to solve for molar mass, you just rearrange the variables again. So molar mass is density times the ideal gas constant times the temperature over the pressure. And if you look at the way these are going to cancel, because here are the units, grams over liters, liters times ATMs over mole K, this is the R. So this would be your density, and here's your temperature, and then here's your pressure. So if you're looking here at the units, the liters cancel, the Kelvin cancel, ATM cancel, and you're left with grams, you're left with moles, which is the measure for molar mass, grams per mole. So if you can't memorize one of the, if you can't derive them, I would memorize one version of the equation so you can solve for density and you can solve for molar mass. You need to be able to do both. Like for instance, in this equation, what is the density of F2 at STP in grams per liter? Well, density equals the pressure times the molar mass over the RT. I pull that equation out. Now all I have to do is plug and chug. Remember, STP is 1 atmosphere, 273 K. You do need to know the values of standard temperature, pressure, but these are on your formula sheet. You have them there for you to look at. You don't have to memorize them, but you just have to know standard temperature, pressure is 1 atmosphere, 273. Look at your formula sheet to plug that in. Now that we have all this, we can go ahead and plug and chug. Density equals the pressure times the molar mass over the ideal gas constant times the temperature. Plug in your values. The pressure is 1 atm. The molar mass of F2, I look at my periodic table. F is 19 grams per mole. I multiply that by 2 and that gives me 38 grams per mole. And as stated before, for molar masses, we usually go out 2 decimal places to the right. On the bottom here, since I'm using ATM as my pressure, my standard pressure, now you could have done 760 millimeters of mercury, but it's a much bigger number to work with. That's why I stick with ATMs usually. So down here, this would be 0.08206. This is the liters times ATMs over moles times Kelvin. And then my temperature, 273K, which kind of gives me my basis here. 1 ATM, 273K, those are usually the typical values that are written on your formula sheet. And it really doesn't matter. You could probably get away with 2 significant digits here, or 3. I would go with 3 because I'm kind of base it off of these values, even though there isn't a measured value in here. When in doubt, go with 3. It's usually within 1 digit of being correct at that point anyways. So 1.696 is the calculator answer. I would round it to 1.70 grams per liter. And just to verify that everything cancels correctly, let's go ahead and do that. So ATM, ATM, K, K, mole, mole. So we're left with grams and we're left with liters. Grams over liters. Aha! Dalton's laws of partial pressure. Dalton's law of partial pressures. This is a fun one too, because it gets quite intricate. Starts off with the easy thing of, remember Dalton's law. We're talking about a mixture of gases though. Mixture. So like in a container, in some kind of closed container, you might have neon, oxygen, helium, or CO2. Like it's a mixture of gases floating around in there. They're not reacting, they're just bouncing around, colliding with the walls of the container, maybe colliding with each other, but they're not reacting. So that's why we said it's a mixture of gases. So the total is based off of adding the individual partial pressures of each individual gas. And partial pressure notation, like here, if I'm talking about this example, partial pressure of neon, you put the big P and then you put this as a subscript. Partial pressure of oxygen, partial pressure of helium, partial pressure of carbon dioxide. That's how I would write out partial pressure notation. Now the total pressure exerted is the sum of the pressures of each individual gas if they were to be in their container by themselves. So for example, here we have 2 separate containers. One has oxygen, one has nitrogen. They are all the same size, same volume of containers. Oxygen has 159 millimeters of mercury for its pressure in here, based off the number of particles and the temperature and other conditions. We're assuming they're all at the same temperature though. Pressure of the nitrogen, 593 millimeters of mercury. So assuming the particle number and all of that complies with that. If we were to take both of them and combine them into the same size container that they were originally were in, basically all you're doing is taking the 159 and adding it here. And it gives you this value. So it's just additive. So we add the 2 gases together and they give you that new total pressure in the container. This is what we're going to be looking at on Tuesday, is collecting gas over water in an experiment. The apparatus usually has some kind of reaction vessel over here where you have tubing that takes it to the collection area. Now, the collection area could be a multitude of things. It could be an upside down burette. It could be an upside down graduated cylinder. In this particular case, because it's kind of rounded at the top, this would be what we would call an eudiometer, and they also have the markings. They're very similar to that of a graduated cylinder in a burette instead of markings. And that's how you would measure the volume of the gas as it collects. You have this completely filled with water, but the tubing over here lets the gas bubbles come up and then the gas starts collecting and it pushes the water down, and then you can measure the volume of the gas. Now, one thing to remember though, when you collect gas over water, there is a certain amount of vapor pressure of the water floating around in here, because a little bit of it escapes and you have a little bit of water vapor floating around there. So in terms of the pressure, P total here, this is going to be the partial pressure of the water vapor still in there, and also the partial pressure of our oxygen gas. In this particular case, we're collecting oxygen gas. You could be collecting hydrogen gas. It depends on the reaction though. So here, if I wanted to know the partial pressure of just the gas that was coming out of the reaction, I would have to subtract out the partial pressure of the water. Now, water vapor has different partial pressures at different temperatures, but usually you're provided a table where it tells you what the partial pressure of the water vapor would be at that particular temperature, and you subtract it out. Once you get the pressure of the gas, by doing this part, this is the Dalton's law of partial pressure part. Now you have the volume here, that you have that measured volume. You would convert that to liters. And you know the temperature because you're the one doing the lab experiment. You probably have the thermometer out. You know what the air temperature is at that particular time. Now you can find the moles of the gas that's being collected, which you can convert to the grams of the gas being collected. And this is where you can figure out stuff. And once you figure out like, hey, how much of the oxygen was made, you can use stoichiometry to figure out the percent yield. You can use stoichiometry to figure out, how much of the limiting or how much of the excess reactants is left and all that too. So this is a particular setup where not only do you find information about the individual gas you're collecting, but that also can be used to do calculations to find information about other things in the reaction. So we will be looking at some stoichiometry in this particular lab as well. But the Dalton's law of partial pressure part is subtracting out the water vapor to get your gas. Aha! Now, Dalton's law of partial pressure isn't as simple as just adding up partial pressures all the time. Seen this problem in different AP exams where they give you this big vessel and they have different sizes. One bulb is larger than the other. So it tells you here, consider the following apparatus containing helium, both sides, 45 degrees. So temperature's constant, we know this, that's good, temperature's constant. Initially the valve is closed, and it tells us the helium over here, okay, 2 atm, 9 liters. Here's our switch. That's going to open when the valve is open, okay? Then the two sides of the helium are going to be able to mix. So we're going to do the one side as being the red helium. We'll make this side the blue helium. So we'll differentiate that way. Now, this is the pressure exerted when we're on 9 liters of volume. So this pressure, this is volume. Over here, the pressure and the volume of this side of the blue helium, call it the blue helium gas. When I open this valve though, what is going to change? 9 liters originally for this gas, but now it's going to be able to creep over here to this side. When I open this valve, this side gas is going to be able to creep over here to that side. So when I open the valve, the gases start to mix and they have more space to spread out. So the volume is going to change. When the volume changes by opening the valve, that's also going to alter my two partial pressures. When I make the volume get bigger, what's going to happen to my partial pressures of my helium? They're going to decrease, exactly. So before I even can get to calculating the total pressure, I have to figure out their new partial pressures once I've opened the valve. So let's start over here with our blue helium. We have P1 V1 equals P2 V2. We're starting off with 3 ATM. We're going to have 3 liters is our original volume. Now we don't know what the new partial pressure is, but we can figure out what the new volume is. What is going to be my new volume when I open that valve? I have 3 liters over here. I have 9 liters over here. So my new volume is going to be what? This valve is now open. Gas is flowing either direction. So yes, my new volume is going to be the 3 plus the 9. That gives me 12 liters, or 12.00 liters. So this is going to be 12.00 liters. So my new partial pressure of the helium over on this side, which I'm calling the blue helium, is going to be 9 divided by 12, because 3 times 3 is 9. So this is 0.750 ATM. So this is the new partial pressure of this blue helium on this side. Over here, though, let's take a look. Let's do the red helium side. Same deal, though. Have to figure out the new partial pressure because it's starting out at 2 and it's at 9 liters. And we're going to increase the volume to 12. So 2 ATM times my 9 liters is going to give me my new pressure times the 12 liters. So basically I get 18 divided by 12, because 2 times 9 is 18 divided by 12. This gives me 1.5 ATM. So this is of my red helium. So we're looking here now, we have the new partial pressures. We have the one of the blue, the one of the red. Now we can just add them together. So I have the total is going to be the partial pressure of the helium on the red side plus the partial pressure of the helium over here, what I'm calling the blue side. So if I add those two together, I get 1.5 ATM plus 0.750 ATM. Go out 2 decimal places due to significant digit rules here, and we end up getting 2.25 ATM. So this problem is a little bit longer because you have to use Boyle's law to figure out the new partial pressures before you can add them together. I've seen this apparatus before in questions, so I wanted to show it to you where if they say open the valve, well then the volume is going to change. If the volume changes, then the partial pressures are going to change. So do that before you add them together.